Now, you may find it strange that I'm talking about how stars end their lives. Don't we know that? And in a qualitative sense, we do. But a lot of our observations, a lot of what we know is actually really more based on what we know from observations. There's still big steps, big gaps in our understanding, theoretical understanding, of what stars do at the end of their lives, both for low-mass stars, like the Sun, as well as massive stars. And the 2 points I want to address later in my talk are, one is, how do low-mass stars eject their envelopes, and how do massive stars explode? I will start with giving you some of the observations we know, then give you a brief summary of some of the basic principles of stellar evolution for those of you who are not astrophysicists, and then talk about various dynamical instabilities and core collapse modeling, and how ultimately how we may be able to test that using gravitational-wave detections. As I mentioned at the bottom, there are lots of connections to this work here, and this is of course one of the reasons why I'm here to talk to all of you guys here. Now, to start with, I show you this picture because it's pretty. It's a collage of planetary nebulae from sky and telescope. And what you see here, well, mostly planetary nebulae, I don't think all of them are. And that's the material that's ejected by a star at the end, low-mass star at the end of its life. So in most of these objects, you see these ejector, in this case very shell-like, and at the center of that you have a white dwarf. A white dwarf is the remnant of stars like the Sun. They're supported fully by electron degeneracy pressure and therefore are permanently stable. So this is what the observations tell us. They tell us that low and intermediate mass stars at some point very efficiently eject the rest of their envelopes. And so this is a relatively fast phase. And the way this is usually described in the literature is that at some point stars develop what's called a superwind, a mass loss phase where they lose envelope mass very rapidly at a rate of about 10 to minus 4 solar masses per year. So if you have a solar mass left, it takes 10 to 4 years to eject the rest of the envelope. And by astrophysical standards, that's quite rapid. And you're left with a remnant at the end. We know a lot about the remnants, the white dwarfs. They have a typical mass of 0.6 times the mass of the Sun. And I show you here a typical, a recent white dwarf mass distribution. And you see this very striking peak at just 60% of the mass of the Sun, and the Sun is actually going to become a white dwarf of roughly that mass. But what we don't understand really is what triggers these superwinds, and also why is there this characteristic mass of 0.6 solar masses. Just as a note, I already said white dwarfs are supported by electron degeneracy pressure. There's a maximum mass at which electron degeneracy pressure can support the gravity of the object, and that's called the Chandrasekhar mass, which is 1.4 solar masses. So that's way larger than this typical white dwarf mass. Of course, you see there is a tail towards more massive white dwarfs, but that's not the majority. So that's what we know for low mass stars. We also know what massive stars do. At least some of them explode. This is a famous picture. This is a supernova 1987A. And supernova, as the name says, nova means a new star. Supernova means a very bright new star. And this star suddenly appeared in 1987. And, well, it's a famous supernova because it was, well, in our neighborhood. It was in a large magnetic cloud and was the first naked eye supernova since 1604. So supernovae in our galaxy are quite rare, And so this was one of the big events people have been waiting for. Now, since it was so nearby, we know actually quite a bit about it. We also know, in fact, what star exploded, because this is a pre-supernova image, and this arrow points at a particular star. And the star that exploded was not the type of star that was supposed to explode, and that was already a big puzzle. Now, in our galaxy, supernovae of this type occur typically once every 100 years, but there are about 100 billion supernovae. So in other galaxies, there's supernovae, well, about 10 supernovae every second. Now, these days, there are big surveys, and we find thousands of supernovae every year. And in the next few years, there will be even bigger surveys, and then there will be tens and hundreds of thousands of supernovae every year. I don't know what we are going to do with them, but that's for another day. So some stars, at least, explode. But let me come back to 87A, because this is supernova I've worked on for 36 years. And it was a very unusual one, so I should make a few comments. As I already said, it was the first naked eye supernova since 1604. And one of the dramatic early events was that neutrinos were detected. There were two main detectors, Kamiokande and IMB, that discovered about 17 neutrinos. The arrival times are indicated in this figure down here, so they arrived over a period of about 12 seconds. Now, these neutrinos are probably the best studied neutrinos in the universe, or on Earth, because they have confirmed that the supernova was triggered by the collapse of a massive star. Not only that, that you formed a neutron star, because you can deduce from these few neutrinos that the energy in the neutrinos was about 3 times 10 to the 53 ergs, and that is the binding energy of a neutron star. So this was a very dramatic confirmation that these explosions are indeed triggered by collapse of a massive star to a neutron star. But in most other respects, or many other respects, it was a very unusual supernova. I already mentioned it was a different type of star than one expected. It was a blue supergiant, not a red supergiant. And in the picture on the poster, you saw this triple ring nebula, which is a picture taken by the HST in the early days. The supernova is only the ejector of the supernova at the little spot in the center. All this other material here, which is glowing because it was ionized by the supernova, was actually ejected 20,000 years before the explosion. And, well, why would a star do such a thing? I mean, you naively would expect a star is a spherical object. Why is it ejecting it in this very funny way? Well, the answer, and I won't go into any details, I think, is that it wasn't a single star, but it was a binary star. In fact, most massive stars are not single stars, like the Sun, but are in binary systems and interact directly at some point during the evolution. In this case, we think that the star merged with another star, and this happened about 20,000 years before the explosion, and that this produced the beautiful nebula. And we have modeled this in detail. We see the model we came up with does reconstruct, or does reproduce the model, the observations quite well. If you want to know more about it, come to me and we can chat about it. But of course, Alexander and Athira Menon have also worked on this recently, so they may have told you about it. Okay, now let's come back to stars. There's one star you all know. That's the Sun. Well, how does this Sun work? First, what is a star? A star is a self-gravitating object in dynamical equilibrium where the gravity is balanced by the internal pressure. The internal pressure in the case of the Sun is thermal pressure, so the interior of the Sun is hot. Of course, at the same time, the Sun radiates radiation from the surface, so it loses energy. In fact, in the case of the sun, it would take about 10 million years for the sun to radiate away all of its energy. But we know the sun is much older. We know the sun is about 4.6 billion years old. So a star like the sun requires an energy source, and that was a big puzzle about 100 years ago, but now we know the energy source is nuclear fusion. Right in the center of the sun, you have the fusion of 4 protons to 1 helium nucleus at a typical temperature, at a temperature of about 50 million Kelvin. Now, in this process, roughly 0.7% of the rest mass energy is released, and that powers the sun. At some point, the sun will run out of hydrogen, and as we'll discuss in a minute, it will heat up until the temperature becomes hot enough in the center, about 100 million Kelvin, for it then to start to burn helium. In fact, it will fuse 3 helium nuclei to 1 carbon-12 nucleus. The efficiency of helium burning in all subsequent phases is much lower. It's only about 0.1%. So, and a star that's in a nuclear burning phase is most likely in the hydrogen burning phase, and spends most of its life there. Now, the sun at the moment, I said, is 4.6 billion years old. It has actually burned half of its hydrogen in the center, so it's right in its middle age. But in another 4 billion years or so, it will have used up all of its hydrogen, and it will still continue radiating. So what happens then is that the star starts to contract, releasing gravitational binding energy, gravitational energy. Part of that gravitational energy goes into the radiation you see, and the other goes into heating the core. And this is what I said before. You heat till at some point the temperature is high enough to get the next burning phase, which in this case is helium. And this is sort of the governing principle of the evolution of stars. You get contraction phases and burning phases, except that in the case of the sun, after helium burning is over, that's the end. Because by that time, the sun will have developed a carbon-oxygen core, which is supported by electron degeneracy, and that's it. It will end its life as a white dwarf. For more massive stars, that process of contraction and burning phases continues. After helium burning, you get carbon burning, then there's a short phase of neon burning, but then there's oxygen burning, and later silicon burning. But the end product of all of these burning phases for massive stars is that at some point you form an iron core. Iron is the most tightly bound nucleus. So from fusing or fissioning iron, you can't gain any more energy. So there's no more any nuclear energy source. And if that iron core is not stable, I mean, if it's larger than the Chirpmask mass, the only thing it can do is collapse. Okay, so this is sort of the background. If you have any questions at this point, please don't hesitate.
Can I ask a question?
Yes.
How fast is the white dwarf rotating when it first forms?
Slow. I can't give you the exact number at the moment, but it's probably minutes or longer.
Right.
Hours, probably.
I mean, it's easy to calculate. I've just never calculated.
No, it's not that easy to calculate.
Oh.
That depends on the angular momentum loss.
Yes.
And stars lose angular momentum efficiently.
Sure.
Right? So if in the giant phases we're rotating as a solid body, then the period you would be talking about would be years. So it's not quite so straightforward. Anyway, this is sort of the nice cartoon again. that summarizes the two evolutionary paths for low or intermediate mass stars. They burn first hydrogen, then later they actually become big red giants and somehow lose the envelopes, and the mass stars are the same, except at some point they run out of nuclear fuel and explode. So now to return to the question, what happens to a star when it develops a big envelope? And that starts with an energy balance first. What's the total energy of a star? Well, there's first the gravitational energy, and there's the internal energy of the star. For a star like the Sun, the gravitational energy can just be estimated as the total potential energy is of order gm squared over r. The internal energy will be of the order of the thermal energy, something like 3/2 times an average kT times the number of particles. The total energy in the case of the Sun is roughly half of the potential energy. So it's negative, and therefore it's tightly bound. Now, when you start to get a star that gets a big envelope, and I'm talking about stars that are now perhaps 200 or 300 times the size of the Sun, you also have to take another energy source into account, and that's the recombination energy. That's the energy that's released when ions recombine. So when hydrogen recombines, that's 13.6 electron volts. If you include that recombination energy as an energy source in this equation, the total energy can actually become positive. And in fact, it will become positive if you increase the radius enough. Now, this was actually something that has been known for a long time. This was first pointed out by Ludwig Biermann in 1938, where he then concluded that very large stars cannot exist. They are not dynamically stable. Now, what does it mean you have a positive energy? Well, it means that you only, if you do nothing to the star and the ionization doesn't change, then you don't need that term, and the star is perfectly stable. But if you now push the envelope, and in the process, now hydrogen can recombine, or helium, you need to include that energy source. So if you give the envelope a push, in principle, you can eject it all the way to infinity, well, without any problem. If energy is conserved. Now, this idea was picked up by Paczynski and Tsiolkovsky in 1968, where they argued, well, this may be the point when stars, big AGB stars, lose their envelopes. Now, we kind of rediscovered that, Jonathan Hahn and I and Peter Egelin, in 1994. And what we then did is we just calculated these extended AGB stars and looked at the point when the binding energy, including the recombination energy, becomes 0. And then we assumed, if you now take off the envelope, what is the core mass that's left over? And that's what you get. That's the solid histogram. What you also see is a dashed histogram, which was the best observations we had at the time. Looks similar to what I showed you earlier, but this was a few years earlier. And, well, they're identical. Now, why is that remarkable? Well, it is remarkable because we didn't put in any free parameter. And we just calculated HB stars and asked at what point do envelopes have 0 energy. Take the core mass at that point, and you perfectly reproduce this peak at 0.6 solar mass. Now, so this is why I think this is the ultimate answer, but of course it's a bit more complicated. We know that stars do not eject the envelopes in one big go. I told you observationally we see there are these things we call superwinds. And so what we think probably happens, or what we speculated, is that at this point you probably start to develop these very strong winds, and even though you don't lose the envelope instantaneously, you lose it quite rapidly, and then would still get a similar mass distribution. Now, of course, after Pashinsky, Tsiolkovsky proposed that, there was, of course, quite a bit of work on this in the late 70s, particular work by Tuckman, and Barkat, where they were actually trying to confirm this. And I think I need to blow up this figure a bit, because the scale is a bit small. And what they were calculating was the dynamical structure of such envelopes as a function of time. So these are different mass shells. You see, this is the radius coordinate. So the outer coordinate is the surface. And what you see are these pulsations, these radial pulsations that grow in amplitude. And whenever you have an error, they actually find a dynamical ejection. So after an ejection, the pulsations die down a bit. And then after 40 years ago or so, you get another ejection. So that, face value, you might think confirms this speculation by Pashinsky. Well, it's a bit more complicated because these were adiabatic calculations. At the time, they were actually quite difficult. And in reality, and this was pointed out by Fox and Wood in 1982, when these envelopes expand a lot, they also radiate a lot. In fact, the radiation loss timescale becomes shorter than the dynamic timescale of the pulsation. So what that means is that rather than going into expansion, a lot of its energy is just radiated away. And so they concluded that when this is taken into account, that you wouldn't get any of the ejections. Now, there were a couple of papers in the early 90s on this, but this is basically where this picture stayed for a while. Now, and this now comes where our new work comes in, and this is PhD work of one of my students in Oxford by Matthew Clayton, who looked, in fact, at the dynamical stability, the dynamical mass loss from unstable giant envelopes. And what he did is a very systematic study, high dynamical study in 1D of such unstable giants. But these were proper stellar models, so they included all the radiation, which Tuckman et al. Didn't have. And well, he applied that to different types of systems. And I will show you some of the results in a minute. Here's some technical details and caveats, but that's more for the experts. Now, the first calculations I want to show are not actually for AGB stars, but for so-called common envelope systems. And I don't know whether you've heard about this. In many binary systems, when one star becomes a red giant, it can actually engulf the companion star, and then the companion star starts to spiral into the giant envelope, and that releases orbital energy and may eject the envelope or not. This is sort of illustrated in this calculation. This is for a 1.6 solar mass object that has an initial radius of about 200 solar radii, and these are different radius coordinates for given enclosed masses. And the assumption in this model is that you have a companion star at this location that spirals in, and as it spirals in, it releases orbital energy, which heats the envelope, and as you can see in this calculation, the envelope expands by a factor of 2 or 3. And in this phase, we have the steady energy source in the center from the spiraling in binary that deposits energy in the envelope, and the question is, what does it do to the envelope? Because these envelopes also have positive binding energies by the definition I gave you before. And indeed, what he found, what he did is he put in a 1D structure, put in the energy source, and again he gets this, what you see here, the blue curve is the radius, it's the surface radius. You see this big radial pulsation. The red line here is the total mass. So in this top calculation, nothing happens. You get these big pulsations, but the mass is constant. But depending on what the envelope, what the energy is, and the case I want to look at is perhaps this case here. For a certain amount of energy input, gets these pulsations, but then once in a while gets these bigger pulsations where in fact he ejects mass. So this the total mass drops by about almost 0.1 solar mass. Then you have another few pulsations, and then again you get an ejection event. So you get these repeated dynamical ejection events that in which you typically lose up to 1/10 of a solar mass, but you quickly get rid of the envelope. In fact, the bottom, this is a longer calculation. Again, it starts at 1.6. It goes on for 1,000 years. And you see these repeated phases where you have lots of ejection events. Then there's a phase where you don't have any ejections. And then they turn on again, and so on. So you get sporadic ejections. But if you time average it, it gives you a very large average mass loss rate. In our case, it's about 10⁻³ solar masses per year. So it's even higher than what I suggested before the typical superwind mass loss rate is. Okay, what is actually happening? I can go into this in great detail, but let me just give you the basic picture. The evolution of the radius and also the ejection is entirely driven by the recombination of hydrogen and helium. When you get pulsations, and there's some equilibrium point and you have pulsations, and at the large radius, most of the material, most of the hydrogen and the helium is neutral. As you compress it, you start to ionize hydrogen and helium, this phase, but that takes energy out of the pulsation. And so that reduces the pressure counteracting the compression, and so it overshoots. Then as you expand again, you give back that energy, you accelerate the envelope, and you overshoot. So you get a typical instability. It's a growing radial pulsation. But once in a while, the compression is strong enough that when you accelerate the material on the expanding phase, it's enough to actually eject it, to eject a shell of material. This is in fact, you see here in more detail. This is one of these phases where you have this pulsation. It's the compression phase. As you plotted the entropy, you see this increase in entropy where there's a compression shock and hydrogen helium is ionized. And then in the expansion, you get a lot of acceleration right at the beginning, and it ejects this shell of material. This is the velocity over the local escape speed. Now, as you could see, it doesn't always happen, because it actually, one thing it requires is that the whole pulsation is coherent, so that you get very deep compression. The other thing that shouldn't happen, it should also not become too big, because if it becomes too big, then the radiative losses that Fox and Wood talked about become catastrophic. And then a lot of the pulsational energy is just lost in radiation. And so this explains the individual events, but also why it's not regular, why it's episodic. Now this was for a common envelope system, but we find the same actually if we look at AGB stars. AGB stars now are red giants that have a carbon-oxygen core. They're very interesting because they have two possible burning sources, hydrogen burning and helium, which can't occur at the same time. So you get this phenomenon of thermal pulses, and I'm sure Amanda And John will have talked to you about that. But that's not the point of this figure. This figure also shows that as you evolve on, as the stars become bigger and the binding energy becomes smaller, at some point you start to get these pulsations. Initially there's no mass ejection, but then at some point you do start to get mass ejection. Again, it's quite rapid, and it really suggests that once these dynamical events occur, you can lose the rest of the envelope that you have at that point very quickly. And that would make this consistent with explaining the white-dwarf distribution as we were arguing in 94. Now,
Philip,
yeah.
do you either get a complete injection, that is, it goes to infinity,
Yes.
or you get the oscillation? Does it ever just go a little way out?
Oh no, it goes a little way. You don't eject all of it. Right? So, this is the whole envelope.
Yeah.
Right? It's only this layer that's being ejected. So it's only the outer layer. So you see this material here goes to infinity, but you see material falling back. And so it does fall back. So you again get an accretion shock. And in fact, this is quite non-coherent. And so the next time, the compression is not as deep. So that's why you also don't get, in this case at least, no 2 ejections in a row. Which is also consistent with what actually Tuckman already found. So the picture is not fundamentally different, except that we do have the radiational losses in our calculations. Now, this also, so this is for AGB. So it also works for more massive stars because it doesn't say anything about the mass. Indeed, even for red supergiants, we find similar behavior. This is for a 25 solar mass star that at some point starts to develop these pulsations and these mass-losing ejections, these ejection events. Of course, massive stars don't end the evolution that way. They end it because what happens in the core. And so that now lets me return to the evolution of massive stars. Massive stars end because, the very massive ones, because at the center you have an iron core which no longer can produce any energy, and so all that can happen is that the core collapses. Now, how does this collapse work? Well, basic principle is relatively straightforward. You have an iron core that collapses. In the collapse, the temperature rises. You photodisintegrate first the iron to helium and then later to protons and neutrons. And at some point, you reach nuclear densities where the neutrons essentially touch each other, and so the strong force becomes important, stopping the collapse. But by that time, you have what's called a proton-neutron star, object that's mainly consists of neutrons and some protons and electrons, and has a radius of about 30 kilometers. Now, ultimately, the energy source here is gravitational potential energy, because that's what a collapsing core does. And eventually, it has to be the total binding energy of the neutron star. And the binding energy of a neutron star is of the order of 10% of its rest mass energy, which is about 3 times 10 to 53 ergs. Now that's a lot of energy. In fact, that's about 2 orders of magnitudes more than what you see in a typical supernova. In a typical supernova, the energy is about 10 to 51 ergs. The problem is that most of this energy comes out in the form of neutrinos. Neutrinos, as you know, couple very weakly to matter, so they escape freely. And for a long time, it has been a problem. How might you be able to capture some of those neutrinos to stop this collapse of the outer layers and convert it into an expansion, into an explosion? Because supernova is an explosion, not an implosion. Now, this has been a big problem for many decades, and until a few years ago, what happened, sometimes they exploded, but then when the physics improved, they didn't explode anymore. Of course, the person who should talk about the history is Bernhard. But I think that at least in the last few years, the supernova models actually work. And the basic idea today, not a new idea, but the basic picture is that of neutrino-driven explosions. And this is sort of a blow-up of what happens near the proto-neutron star. The proto-neutron star cools and emits a lot of neutrinos. You still have material falling in, which causes an accretion shock. But behind the accretion shock, you have a dense region where neutrinos can actually deposit some of their energy. It's called the gain region. And if you accumulate enough energy in that gain region, you may be able to revive the shock and converting it from an accretion shock into an outgoing shock that then ejects the envelope. Now, that's the basic idea, and that now seems to work. It still takes a long time. You have to typically wait a couple of 100 milliseconds for accumulating enough energy to reverse the shock, which is a long time because that's about 1,000 dynamical times of the neutron star. So, in fact, some people have criticized this model for that reason. Nevertheless, I think it now seems to work. And what you can see from this is that the whole process is a threshold process. You have to wait till you have accumulated enough energy and to overcome the binding energy of the still infalling material. So it's directly related, the energy we need is directly related to the binding energy of the outer core, which for an iron core is typically 10 to 51 ergs. So that's where that characteristic energy scale comes from. Now, as I said, for at least 5 years, the three-dimensional simulations, which Thomas Janker, Bernhard Müller, and many others have done, are successful in exploding the star. They may still not produce quite the energy that's observed, but there are many reasons how that could be changed. But in any case, they do explode. If you want to get more details, you should ask Bernhard. Bernhard, is that roughly right?
That's absolutely correct. I nodded.
Good. Anyway, so this is actually quite, in this sense, we are actually now in quite a unique situation. We can actually, for the first time, try to connect stellar evolution theory with supernova explosions with their remnants. Specifically, we can ask questions, is what are we left with? Is it a neutron star or a black hole? Up to date, people are using guesses, essentially. Good guesses, but guesses. You can also ask, what's the strength of the supernova? Is it a standard supernova, or weak or no supernova? And I should say here, I'm now only talking about normal supernovae. I'm not talking about any of the more exotic stuff, which I've listed up there. And to do this, what we have done in the last few years is really trying to do this, connecting pre-supernova evolution with supernova models. And this is work led by Fabian Schneider in Heidelberg, who's constructing the pre-supernova structures, and then combine that with Bernhard Müller's supernova model, which is a simple 1D model, but it's designed first to reproduce what you see in the 3D simulations, and it's also calibrated to be consistent with the observed observations. And yeah, so this is, I think, is really, this is, I think, the first. There are other people, quite a few other people also working on similar things, but we have probably taken it a bit further than most of them by actually trying to make a specific prediction. And that's what I want to show you at the end. And so what we've done is we've calculated selection of massive stars, single and binaries, but that's not what I'm talking about today. And you can describe the pre-supernova structure of the star by using something called the compactness. I mean, I told you before that the neutrino-driven supernovae involve a threshold process, so they depend on the binding energy of the inner core. So it makes sense to look at the binding energy in some form. And this is what this compactness parameter does, which was introduced by O'Connor and Ott. It's this quantity. It's m in solar masses divided by r in units of 1,000 kilometers. And it's usually evaluated at a mass coordinate of 2.5 solar masses. But what this really is, it's just gm over r in some funny units. It measures the gravitational potential at that particular mass coordinate. Why at that mass coordinate? And should it not depend on more details? And the answer is probably yes. But we actually find that is a reasonable parameter, and we have no no ulterior motives here. It is reasonably good in predicting the fate using, for example, Bernhard's model. It's a model. This parameter can be used for explodability in the sense if it's big, that means the star is very compact, it's harder to explode the star, and if it's small, it's more extended, so it's easier to explode. Irrespective of whether you can use it for explodability, it's a good way of actually quantifying the structure of the star. And that's what we have done here. This shows the compactness for stars, single stars and strip stars, but I'm not going into those differences, as a function of the carbon-oxygen mass, so the core mass, which is more useful. And you see some interesting behavior. You see at low CO masses, you get low compactness, and then at a characteristic CO mass of 7 or 8 solar masses, it goes up a lot. And then it goes down again. And then at much higher mass, it goes up again. This behavior we obviously call the compactness peak, because it's a peak. And just taking the arguments about explodability would suggest that stars in this compactness peak form black holes, while the objects to the left and to the right form neutron stars. Now this behavior actually was already found, Alexander around? No. He already found a similar behavior when he was looking at the iron core masses actually. And he also found that there was an iron core peak roughly at the same location. So it's not, you're not the first one to find it, and then for anyway, anyone else who's looking at compactness over this mass range finds something very similar. Okay, so what does this mean? Well, the other thing you see here, I've shown you this peak at solar metallicity and also at a much lower metallicity, which is the 10th of the metallicity of the Sun. And the behavior is very similar. In particular, the compactness peak is essentially in the same location. What happens then later is a bit different. We will not discuss that, but that's also not important for the point I'm trying to make next. There's a prediction that there is this unique compactness parameter which is roughly independent of metallicity. This is independent of the explosion model itself. Now, if we now apply Bernhard's model, we can make a prediction of the masses, and I'm now showing you only the black hole masses. Only look at the bottom two panels, and you see you get a peak from the compactness peak, you get a typical black hole mass of around 10 solar masses. But because beyond the compactness peak you don't get black holes, you then get a gap. And then at 15 solar mass or so it rises again. And if you go to the low metallicity, you get something very similar. The main peak is essentially the same mass. And then again, you get a gap of or more or less also the same mass. And then you get, of course, you get, there's a difference here. You get much more massive black holes, but this has to do with the low wind mass loss in these lower mass systems. And that's not what I want to concentrate on now. I just want to concentrate on this peak and this gap. The reason why I want to concentrate on that is because that is something we can now test with LIGO. You know, LIGO, I don't have to explain that. I don't have to give you any background on this here. When LIGO measures the final inspiral of massive compact objects, when I say massive of compact objects, this is an illustration of the final merger of two neutron stars and the gravitational wave signal you get from this. Now this is for two neutron stars, and this shows the spiral in, the gravitational wave signal you get for the last tenth of a second, and you see you get a particular frequency, and that frequency goes up. And this frequency is entirely determined by a combination of the masses of the two objects, which is called the Chirpmask. No, almost entirely. This is the Chirpmask. This quantity combines the two masses, and if you have equal mass, it's roughly 90% of the mass of each component. But the important thing is that this is a quantity you can essentially measure from LIGO. Moreover, LIGO and Virgo is more sensitive to more massive objects, meaning more massive black holes, and so it's particularly helpful in really testing what happens to merging black holes, and specifically can help us in testing this prediction. And what I show you here in this panel is the Chirpmask distribution after O3 as it stands now. And I don't want you to look at the black curve. I want you to look at the faint gray curves. Can you see those? Those are actually the data. Those are the inferred chirp masses for something like 70 events. And if you just look at the data, ignoring the modeling, well, you see there's this concentration chirp mass of around 8 or 9 solar masses. And then you have this gap between 10 and 12 solar masses. So that's in the existing chirp mass distribution. And that is actually perfectly consistent with this. So I would go so far to say, at least unofficially, that so far there's actually some support for our prediction. Of course, these are, I'm not interested in these systems here. So the systems here, they're still talking about fairly small numbers. And we have done some preliminary modeling. We can have some systems in this Chirpmask gap, but we would predict there are far fewer. In any case, this is where we stand right now. And our hope is that we may be able to test this prediction in the next LIGO Virgo science run, which is just about to start, or I've heard from Ilya that they've already made some discoveries, pre-engineering. But in the O4, you will see they should be able to find a few 100, 200 or so more black hole mergers, and then I guess the basic picture should become clearer whether this is the peak and there's this mass gap. And yeah, this is where I stop. Thank you.
This is a Chirpmask, which is a measure of the binary properties, but we have mass distributions, posteriors.
Yes.
Shouldn't you be comparing those with
No,
your predictions?
because I don't trust them. No, that's why I already said, well, don't ignore this curve, right? So this is a model that makes certain assumptions. I think one should go to the data.
No, that's what I'm saying as well. But the data has M1 and M2 of the binary.
I know, but then you know the data ellipses. I mean, yeah, ultimately we should do both, right? But at the moment, I trust this much more because the chirp mass is much better determined than the individual masses. And when people do these reconstructions of black hole masses, they make assumptions that are not consistent with what we think should happen. I mean, like having a smooth black hole distribution, no gap, for example.
Oh, that's the population distribution, but not individual event.
Oh, yeah, sure, that's true. Yeah, sorry. Yeah. I was talking about when you try to reconstruct the black hole distributions. But the event distribution, you're of course right. And yeah, I think at some point, when this becomes relevant, I'm sure we are going to do both. But, you know, yeah.
In the next slide, you talk about your predictions compared with the 04.
Yeah.
Suppose the predictions don't fit the 04 to better than 20%.
That's a good question. Then either Bernhard, who is left, is in trouble, or we are in trouble.
Yes.
I mean, I think something has to go. It has to give.
Yes. So some assumptions have been made which are incorrect.
Yes. Yeah, that's what it would mean. So what we have tried to do is to really do what we think is the best we can do at the moment. Using, I mean, I didn't discuss any of the details, but using the wind mass loss rates that people think are the best today, using overshooting parameters that are consistent with observations and so on. Though this doesn't even matter too much, but.
And if it does fit reasonably,
Yes.
Can I assume everything is spherically symmetric? Because that's what you assume. The rotation doesn't really change anything much, more than a few percent.
For these stars, yes.
So the world becomes more spherical.
Right. It is. But I should say, of course, I was looking at what I call normal normal stars, normal supernovae. There's lots of room for more exotic things, right? Which we know of.
Yes.
You know, gamma ray bursts, superluminous supernovae, and pair-instability supernovae, Alex is very fond of. But these are much, much rarer events. So we are really talking, I'm talking about the dominant events.
Yeah.
And they are more spherical, yes. Even if they originally were in a binary.
Well, that's interesting, isn't it?
I mean, the reason, I mean, you were talking about rotation. The modern view on rotation in massive stars is that all massive stars rotate rapidly initially. But by the time they explode, at least the single ones, have lost most of their angular momentum in the form of a stellar wind, and because there's efficient angular momentum transport within the star. And it's increasingly clear that the dominant angular momentum process that transports angular momentum within stars are magnetic fields. So that's something I think you're interested in. So believed, at least that's the current picture. And that makes the cores of the stars at the time of the explosion more spherical. The explosion itself doesn't have to be perfectly spherical. Because we know that neutron stars get kicks, for example. Yeah.
You talked here about the properties and so on, you look at the Chirpmask and so on, you look at the modeling of the evolution and so on. Do the numbers match up in this? You talked about that you see, you know, X number of supernova per year, etc. You know, if you look out at the mass distribution of stars and so on, do the number actually match up? Do we find everything with the efficiencies that we have, of course?
Now, the number of neutron supernovae for the number of supernovae, we can't really tell, and we don't really know how many of these stars experience supernovae, and we don't have the rates for these massive ones. So there we don't really, and for the low mass ones, we fit by default because that's just related to the star formation rate. But another question is a valid question, valid issue, is this is actually not, I mean the peak is where it is, but this is not, these are not calculated rates at the moment. So I can't tell you at the moment what the ratio of these systems to these systems is. And that, of course, is an important constraint. And in fact, that's one of the things which we have started here with Ilya and Reinhold to actually try to estimate these rates. Because that is another constraint which we haven't yet done. Here we have only done the location, not the rates. And there could be obviously a surprise there. Yes?
This question about the AGB stars, well actually not a question, maybe a comment. I mean they're really dusty objects, and so if you include coupling dust, you might find the mass loss rate to accelerate, or at least to occur earlier than you find, perhaps. But we know that the mass loss rates, we do see AGB stars, I'm not an expert on the observations, but we do see them losing mass fairly early in their evolution, at least compared to when I think
you're absolutely right. I mean, if I just look at this figure here, right? You see here these pulsations here, they don't do much, but here they are quite extended, right? So these pulsations are big enough that you would expect to go into the regime of dust-driven winds. So they should probably start, yes.
If you include coupling with dust, I think that would be very interesting.
Yeah. Yes. No, I agree. This could, actually, could, because if once you start the mass loss, then actually the stars tend to initially become bigger, which makes them more unstable. So there could actually be a direct feedback. So in fact, that's probably, I mean, what observations tell us, because we do see these things that we call dust-driven shells, and they're not as dramatic as this. So you probably start out like that, and then we would argue that at some point you can go into this phase, but that's a much shorter lived phase.
I think the mass loss rates on average are lower as well. I think they're more like a few times 10 to the minus 5.
I was more thinking 10 to the minus 4, but well, it depends. It varies. I mean, Myra is even lower. And
at least for 1 to 2 solar mass. OHIR stars different.
Yeah. Anyway, that's still a whole area which we are actually working on right now, and we should talk about more.
Final one or two questions before you want to let's start with Tyson.
So actually on this plot as well, these, because you've got like pulse 10, pulse 12 written, are those like the star pulsating, or are those meant to be thermal pulses?
These are the thermal pulses, actually. Yeah, I mean, sorry, I didn't go into details. I mean, here you see, this is the evolution of it. You see the thermal pulses there, and so they're just labeling them. And I should point out, as I told Amanda earlier, we are not having any extra mixing, so we don't get any carbon stars and things, which, as you point out, might be another important issue, which could actually be interesting, because you were saying that, that once you get carbon, you should stop the process quickly. And so if the formation of carbon actually helps here, that would be useful.
Last question. So you talk about the role of neutrino heating in driving supernova.
Yes.
Presumably that depends on like the neutrino matter scattering cross section.
Yes.
So there's a lot of like different standard model extensions that increase or decrease that cross section. So can you use these data to somehow constrain that cross section or infer something, or is it just not precise enough?
I'm not the right person to ask that question. I mean, I know though that the supernova people are actually trying to do exactly that. So Thomas Younger's group, for example, they're asking whether if these cross-sections are increased for certain reasons, how much that helps. So I would not use our modeling for that. And I should, as I pointed out, is we did adjust it, Bernard did, adjusted his model to reproduce the right supernova energies. Right? So it's actually already an extrapolation in that sense.
And is the neutrino cross-section that's necessary to reproduce those energies consistent with the standard model? I assume so, otherwise we probably would have heard.
Yes. But at the moment, the self-consistent calculations don't yet produce enough energy. But there are many reasons, that some having to do with neutrino physics, but others having to do with asymmetries in the core. Even though they're roughly spherical, the convection in these shells just around surrounding the core is quite violent. And you might get some asymmetries from
So is that part of the turbulence?
Yes.
Yes. So it hinges on the model of turbulence.
Probably. But these are actually, I mean, Bernard has done some simulations and are large, fairly large scale. It's not small. It's not small scale turbulence.
You say probably, but I think the probability is probably 0.9.
Yes. But these asymmetries actually may have an effect on the core collapse mechanism, which is not what I wanted to talk about, but I think it is. Yeah. But anyway, Bernard is the expert on that. I'll deflect that question.